Alright, so in this video we go over sections 9.4 through 9.7. So this video will be more like a summary of the most important points or key points into vectors. Okay, so first we are going to define what a vector is and how do we find vectors given points, etc. And then we do operations and what some of the operations are really implying here. So, well, a vector is a quantity that has both a magnitude and a direction. It's typically represented by using an arrow. The length of the arrow represents the magnitude and the arrowhead indicates the direction of where that vector is going to. So one of the most rather particular vectors is the vector whose magnitude is 0, which is called the zero vector. Notice in this case we're going to use bold case. Well, and when typed we're going to use bold case letters, but I'm going to use a slightly different notation because I cannot do bold case by hand, by writing. Alright, so I'm going to show you the notation I would use. And then, well, so how do we find a position vector? So we're going to find a vector that passes through the point x1 comma y1 and the point x2 comma y2. Alright, so all we do is find the difference x2 minus x1 comma y2 minus y1. And in this case we use this notation. It looks like diamonds. It looks like diamonds. That's to denote vectors. Alright, so let's do an example and show you how to graph them, how to plot them. Well, so we're gonna find the vector that goes from point 1 to point 2. That actually let's plot -1 comma 2. That's the point 1. And 4 comma 6. That's 1 2 3 4 1 2 3 4 5 6. Alright, so we're gonna find the vector that passes through that point. Alright. So in this case, well, the vector, and actually notice the vector here v, it's in bold case, but I cannot do bold case. What I'm going to do is put an arrow on top of those variables that denote vectors. And in this case, well, I'm going to subtract x2 minus x1, that is 4 minus -1, comma 6 minus 2. 6 minus 2. Oh, it's actually like this. And the vector in this case is going to be 5 comma 3. Alright. So how do we represent that vector? Well, there's another way to represent this vector using i's and j's. 5i plus 3j. And both letters would have had I represents the number that multiplies. I represents, well, in this case the direction in the x-axis, and j represents the direction in the y-axis. Now, well, notice we have these 2 points right here, and it's gonna go like this. However, we need to represent these vectors in a standard position. What do we mean by standard position? Well, so keep in mind, well, again, this is x and this is y. We need to start at the origin, well, and then from there we move 5 units, 1 2 3 4 5 in the x direction and 3 units in the y direction, and that's how we represent the vector. It's going to have the same inclination or the same slope, if you will. Looks slightly different. Well, my drawing is not perfect, but that's the vector. That's the vector v. That's how we plot them. Alright, let's see what's next on the next page. Well, adding and subtracting vectors. Well, that's it's going to be a really short. All we are going to do is simply add and subtract numbers, no more, no less. You know, so we have a couple of points in which, a couple of vectors v, a1i plus b1j, and the vector w, a2i plus b2j. So those are going to be the 2 vectors. Adding the vectors, all we do is add the x's, a1 plus a2, and at the y's. Well, not the x's, but the a's and the b's. And that's all we have to do. It's really not that crazy. So let's do a couple of examples for the subtraction. We would do this basically the same, but with a minus sign. So what are we going to do? Well, so 2y plus 3j. Actually, the number doesn't have the hat. All right. And plus 3i minus 2j, or using the other notation, to 3 plus 3 negative 2. So simply 2 plus 3 equals to 5. 3 plus negative 2, that's 1, which is the same as 5i plus j, 1j. Alright, that's 1. Okay, so for the subtraction, well, I'm going to omit the ij notation. I'm going to use this notation only. So v, which is 2, 3, minus, in this case, 3, negative 2. Okay, so for the subtraction of vectors, subtracting a vector is the same as adding it, but we change the sign of the two components. Changing the sign of the components will change the direction of actual. Oh, I didn't change the sign, and then that's a positive. Changes the direction of the vector or the arrow in this case. Alright, so 2 minus 3, that's a negative 1, and 3 plus 2 equals to 5. Alright, so that's a negative I plus 5j. Alright, well, graphing vectors. So we need to add this both graphically and algebraically. Well, the sum of the vectors in this case, well, we need to position the vectors v and w in a way that the terminal point of the v coincides with the initial point of w. Then the vector v plus w will be the vector whose initial point coincides with the initial point of v and the terminal point of w. Alright, let's go ahead and do that. Well, let's graph let's graph the vector 2, 3. Okay, let's scratch this real quick. 2, 3. So I'm going to go 2, 3. And then from here, I'm going to go 3, negative 2. So 1, 2, 3, and negative 2. I'm going to go in this direction. All right. So again, the addition of these two vectors will be, so that's v plus w. The addition of these two vectors will be that in which the initial of the first coincide with the terminal point of the second vector. In this case, I'm going 5, 1. Isn't it the same? 5, 1. What about the subtraction of vectors? Well, so v minus w, well, v it's still the same, 3, 2, 3. Okay, but then in this case, subtracting the vector 3, negative 2 is the same as adding the opposite, adding negative 3, 2. So from the terminal point of the first vector, I'm going to go 1, 2, 3 units to the left and then 2 units up. Alright, and then from here I'm going to go the initial point of the first vector to the terminal point of the second vector. Alright, and what's that vector? Negative 1, 5. Negative 1, 5. Negative I plus 5j. Alright, let me make this look like a j. Alright, let's look at other properties of vectors. Well, so we can multiply vectors by a scalar, not by any number. So alpha is a scalar, a real number, actually not a complex number. V is a vector, and the scalar multiple is defined as follows. Well, if alpha is a positive value, well then alpha v would be a vector whose magnitude is alpha times the magnitude of the v, and the direction is the same as in v. On the other hand, well, if alpha is a negative number, well, alpha v will have a magnitude that is the same magnitude as in the previous point. Well, it's absolute value, because I mean the magnitude is supposed to be a positive value. That's why we have this absolute value bars, and then that times the vector of magnitude v, but in this case the direction is opposite to that of the original vector, because in this case the coefficient will be negative. Well, then if alpha equals to 0, we're going to have the 0 vector. Alright, then the magnitude of the vector is defined as, well, these double bars that look like absolute value. Double bars mean magnitude, and it's the square root of a squared plus b squared. And well, I mean, like, where is that coming from? Well, so keep in mind that a vector v whose components are a comma b, all right, that's a in the x direction and b in the y direction. Well, the magnitude of the vector would be basically using Pythagorean theorem. So the magnitude of the vector, that's the square root of a squared plus b squared. That's where it comes from. Another piece of information that we care about is finding a unit vector in the direction of v, and we obtained that by dividing the components of the vector by its magnitude. What about that unit vector? So let's say this vector has a magnitude of 5. Okay, this one has a magnitude of 5. Well, a unit vector would be a vector whose magnitude is one that has the same direction as the given vector. Well, we're gonna see about that in an example right here. Well, so let's do some operations with vectors. We have a couple of vectors, 2i plus 3j, and vector w 3i minus 4j. Let's find each of the following. Well, 3v, all we do is 3 times 2, 3, and all we do is 3 times 2, which is 6, and 3 times 3, which is 9. So, and then we rewrite as 6i plus 9j. Keep in mind we have two different notations. 2v minus 3w, so 2v minus 3w. So that's 4, 6. For 2 times 2 is 4. 2 times 3 is 6. 3 times 3 is 9. 3 times negative 4. Be careful, I'm not multiplying, I'm not using the negative here. That's a negative 12. And then all we do, 4 minus 9, that's a negative 5. And 6 minus negative 12, that's 12 plus 6, that's 18. And if we use i's and j's, negative 5 I plus 18 j. Alright. The magnitude of v, so we're going to find the square root of 2 squared plus 3 squared. Alright. 2 squared, which is 4, plus 3 squared, which is 9. And that's the square root of 13. And this one cannot be simplified any further. Find a unit vector in the direction of v. Well, so this vector is square root of 13 units long. So what we do to find a unit vector in the direction of v, we do the vector v divided by the magnitude of the vector v. So the vector v, which is 2, 3, divided by its magnitude, all we do is divide 2 over square root of 13, 3 square root of 13. And then we can change this to i's and j's. So you change i's and j's, so 2 over root of 13i plus 3 over root of 13j. Final answer. Actually, if you find the magnitude of this vector, that is 2 over root of 13 squared plus 3 over root of 13 squared, you should get 1 as the magnitude. So as you can see, this is really easy arithmetic operations, adding, subtracting, multiplying. But I mean, really what they mean, what the operations mean, it's what matters. All right. The dot product, so that's one of the two types of vector multiplication, the dot product. So if we have the vector v a1i plus b1j and the vector w a2i plus b2j, so the dot product is defined. So the dot product, which is described with a dot, well, it's gonna matter. All we do is multiply the two components a1 with a2 and then add what we obtained from multiplying b1 and b2. But ultimately, what does this dot product represent? Well, the dot product is a directional multiplication. That is, the result is how much stronger we have made the original vector v, which could be positive, negative, or 0. And that actually with respect with the second vector. So we have the same vectors here, 2, 3, and 3, negative 4. Let's find out what the vector v, the dot product of v and u is. So in this case, 2, 3 dotted with 3, negative 4. So all we do is 2 times 3 plus 3 times negative 4, which is 6 minus 12, which is negative 6. So in this case, it's the first vector negative 6 times stronger with respect to the second vector. V times itself, 2, 3 times 2, 3. That's 2 times 2 plus 3 times 3, which in this case is 4 plus 9, which equals 13. All right. So if we multiply the vector v with itself, is going to be 13 times stronger than with respect to itself. So I mean, I'm using the word stronger, but I mean stronger with what do I mean by stronger? Well, this has to do more in with applications in physics, because one of the most common applications of vectors, it's in forces. When you look at all the Newtonian mechanics, we deal with vectors with this kind of notation, and this is what this number represents. Let's do the other one. 3, negative 4. 3, negative 4. So that's 3 times 3 plus negative 4 times negative 4. So that's 9 plus 16 equals 25. Okay. So we can use the dot product. We actually need the dot product to find the angle between two vectors. So u and v are two non-zero vectors, and the angle theta, which is an angle between 0 and pi, we're looking for the acute angle only, not the obtuse angle, because keep in mind that vectors, so these are two vectors, my markers are two vectors. Here we have an acute angle, and the largest angle that can be is 180 degrees. But if we go past 180 degrees, we're not looking for this angle right here. We're looking for the acute angle, not the obtuse angle. All right, so the formula to find the angle between two vectors is cosine theta equals the dot product of the vectors divided by the product of their magnitudes, and then in the end to find the angle theta, that's cosine inverse of the dot product and the product of their magnitudes. That's what we get from here. Alright, but typically this is how the formula is presented. Find the angle theta between u and v. These are the two vectors. What do we need? We need to find the dot product, but we need to find the magnitudes first. So let's find the magnitude of the vector u. It's actually u and v here. U and v. The magnitude of u would be the square root of 4 squared plus -3 squared. That's 16 plus 9, which equals 25. The square root of 25, which equals to 5. The magnitude of v, that's going to be the square root of 2 squared plus 5 squared. That is the square root of 4 plus 25. So that's the square root of 29. All right. So now let's write down the expression cosine theta equals the dot product of these two vectors, 4 minus 3 dotted with 2 and 5, divided by the magnitudes, which in this case is 5, square root of 29. Cosine theta then will be, okay, 4 times 2, that's 8. -3 times 5, that's -3 times 5, that's a 15 over 5 root of 29, which equals, well, in this case, 8 minus 15, that's a -7 over 5 root of 29. And then theta would be the inverse cosine of this quantity, -7 over 5 root of 29. And this will be approximately, well, let's do this in the calculator. So second inverse cosine, -7 over, be careful with the multiplication, 5 second root of 29, close parentheses, and then close parentheses for the entire expression, and that's 105.1 degrees. So right, in this case you don't have to express this in radians, degrees are fine. Now let's look at another very important result when it comes to vectors. Well, two vectors are said to be parallel if there is a non-zero scalar, that's supposed to be scalar alpha, such that v equals alpha w. In other words, if a vector, it's a multiple of another vector, then both vectors are parallel. In this case, the angle, another way to say this is if the angle between the vectors is 0 or pi. Alright, well, so in this case, let's look at this example. The vectors v and w are parallel because in this case, the vector v is it's a half of the vector 2. If you divide this by 2, you get 3i minus j. Right? But another way to show this is, well, let's actually find the angle between the two vectors. Yes, and in this case, let me look at this at my notes. Yeah, so let's find the magnitudes of the vectors v. That's the square root of 3 squared plus -1 squared. That's 9 plus 1. That's the square root of 10. And the magnitude of the vector w, that's the square root of 6 squared plus -2 squared. And well, 6 squared, that's 36, plus 2 squared, which is 4, that's the square root of 40. Alright, And then we need to evaluate the formula cosine theta equals the dot product between 3, -1 and 6, -2. Then divide that by the what's this called? Their magnitudes, in this case the square root of 10, the square root of 40. So 3 times 6, which is 18, plus 1 times 2, which is 3, and that's the square root of 400 in the denominator, which equals, so that's 21. Oh, and when I mean -1 times 2 is +2, not 3. So that's 20 over the square root of 400, which is 20. All right, and that equals to 1. And in this case, cosine theta equals 1. So theta equals to cosine inverse of 1. What is cosine inverse of 1? Well, let's find out. So cosine, that's 0. All right, 0 degrees, by the way. Another very important result or definition: two vectors v and w are orthogonal if and only if the dot product equals to 0. What does that mean to be orthogonal? Orthogonal means a fancy way to say angle between is 90 degrees. So they're, in other words, they're perpendicular. Orthogonal, perpendicular, but so the thing here is the perpendicular is typically used for when we're looking at images in 2 dimensions, x and y. Well, in the case in which the perpendicularity happens in 3 dimensions, well, let me try to put these 2 vectors in 3D, or 3 vectors in 3D. Well, we got this. So in this case, the 3 vectors are orthogonal, well, but they're perpendicular pairwise, like blue with pink, pink with red, and red with blue. In general, we call that orthogonality. And then later on, when you take linear algebra, you're going to look at vectors in higher dimensions, like 4 dimensions, 5 dimensions, 11 dimensions, a million dimensions. Yes, you may look at those kind of vectors, and yet you're going to look for orthogonality between 1,000 of vectors. I mean, even though it's impossible to visualize the body represented by 1,000 dimensions, well, that's something else. But when we look, but I mean, vectors that represented in such dimensions happen to be also orthogonal. So let's find the vectors, the dot product of these 2 vectors. So 2, -1 dotted with 3, -6. So 2 times 3, which is 6, 1 times actually I think there's a little typo here. This one has to be positive. That's a positive. Well, let me just erase this sign. -1 times 6, that's a -6. That's equals 0. So indeed, these 2 vectors are orthogonal. Okay, let's look at the picture for that. Well, 2 So 2, -1, that's the first vector, and then 3, 1, 2, 3, 4, 5, 6. And if you look at these vectors, I mean, the drawing is not perfect, but still we can see the 90-degree angle between the 2 vectors. So that means these 2 vectors are orthogonal. Vectors in space, well, so that's what I was talking about when I was speaking into more dimensions. So I mean, vectors in 3D, well, ultimately what we do is add one more component. So this is the I component, it's in the X direction, the J component is in the Y direction, and the K component is in the Z direction. And the operations are exactly the same. I mean, there's nothing really Nothing really crazy. Well, so let's do some operations. 2 times the first vector minus 3 times the second vector. So 2 times 2, 3, negative 2 minus 3 times 3, negative 4, 5. So that's going to be 4, 6, negative 4 minus 9, negative 12, and 15. Adding this together, well, we get 4 minus 9, that's a negative 5. 6 minus negative 12, in other words 12 plus 6, that's well, it's 18. And negative 4 minus 15, in other words, that's going to be, well, addition of two negatives, negative 19. So that's just one example of operations with vectors in 3D. Nothing new, just adding a third component, more operations. The dot product, let's find out what the dot product is going to be. 2, 3, negative 2. 3, negative 4, 5. So this is going to be, well, 2 times 3, which is 6. 3 times negative 4, which is negative 12. Negative 2 times 5, which is negative 10. And in this case, the dot product will be negative 12 minus 10. That's a negative 22 plus 6. That has to be, let's see, that's negative 22 plus 6 equals negative 16. Let's find the magnitude of the vector v. Well, all we do, it's exactly the same formula. So 2 squared plus 3 squared, but all we do is square the third component, nothing new. I mean, just one more component. That's a square root of 4 plus 9 plus 4. That's 13 plus 4, that's a 17. The square root of 17. Same for the magnitude of w. Yes, I'm on purpose finding the magnitude of the two vectors because we're gonna need them to find the angle between them. All right, so that's gonna be 3 squared plus negative 4 squared plus 5 squared. Let's see what we get. So that's 9 plus 16 plus 25. So 9 plus 16, that's a 25 plus 25, that's a 50, which is the same as 2 root of 25, or actually 2 root of 5. No, hold on. So that's the square root of 25 times 2, 5 root of 2 otherwise. The angle between v and w, well, in this case, okay, so cosine theta equals v dotted with w divided by magnitude of v times the magnitude of w. Well, but we don't need to do the dot product anymore again, because we already have the dot product here, which is cosine of theta equals, the dot product we calculated here was negative 16. Divide that by the magnitudes, square root of 17 times 5 root of 2. Well, so this is gonna give us a crazy decimal. So let's do the square root of 17. Well, let me actually simply go about, well, theta would be cosine inverse of negative 16 over root of 17, 5 root of 2. Oh, not more arc cosine, simply directly to the angle here in this case. That's going to be inverse cosine of negative 16 divided by open parentheses to make sure all this product is inside of the denominator. That's a very common mistake to not put that parentheses, and then this 5 and this root of 2 would end up multiplying, so make sure to do square root of 17 close parentheses times 2 times square root of 2, and then in this case close parentheses for the denominator, close parentheses for the arccos function. And well, for some reason I'm getting an error in the domain. I don't know why. Maybe I didn't put the correct so there's something wrong over here. Okay, let me double check. 2 times 3, that's 6. 3 times 4, 12 negative. 2 times 5, negative 10, negative 22, plus 6, that's a negative 16. And then the magnitude, so that's 494, 17, and then 9, 16, 25, so that's 25 or 25. So let me do instead, because for some reason it didn't work. Oh, it's 5 root of, I see it. It's 5 root of 2, not 2 root of 2. And that should be 123.2 degrees. Basically, 123 degrees. And then, well, for some reason I didn't type, are they orthogonal? Well, no, not orthogonal. These are not orthogonal because the angle between them is not 0 or pi, or the dot product is not 0. Okay, let's do the last page and see what do we have. For the last page we have the cross product. That's another product we define, and by the way, the cross product can only be performed with vectors in 3 dimensions. It doesn't work with vectors in 2 dimensions. So let's see. So the dot product is defined with 2 vectors, a, I, b, j, c, k. Well, actually a1, b1, c1, a2, b2, c2. All right, and their cross product, which is denoted with a cross, actually with a times, with a cross that denotes multiplication, and is defined by this determinant. What we do is we put the standard positions of the vectors I, j, and k on the first row, and then for the other 2 rows, the second row, we write the entries of the first vector, and in the third row we write the entries of the second vector. And well, we have a formula, b1c2 minus b2c1, blah blah blah. Well, you can use this formula if you want, but I'm going to show you kind of a shortcut to evaluate this this determinant. This is actually a determinant which we're going to go a little bit more in detail in subsequent chapters. I believe chapter 11. So some of the properties, or the most common properties of the cross product are, well, if we multiply if we do cross product of v between v and w, well, if we do the product in the opposite direction, the reverse, we get a vector in the opposite direction. And then if we do the cross product of a vector with itself, we obtained the 0 vector. Okay, and then the magnitude of whatever we obtain is going to give us the area of the parallelogram spanned by the vectors. I'll explain what about it. Now, what does the cross product represent? Well, so we have let me try to do this in 3D. So we have a vector like this, u, or actually v and w. So we are going to find, when we do the cross product, we're going to find a vector that is orthogonal to both of them. So it's orthogonal to V and orthogonal to W. Alright, so let's see. We have a couple of vectors. Let's verify those properties right here. So number one, I'm going to show you how to I'm going to show you the shortcut, if you will. So I, J, K, and then put the numbers 2, 3, negative 2, and 3, negative 4, 5. Bar. So instead of using this formula, what we're going to do, I'm going to repeat the first two columns. And then we are going to multiply diagonal y. So in this case, I'm going to multiply this 5 times 3 times I. What is that going to give me? Well, that's going to give me 15i. And then j times negative 2 times 3. That's going to give me negative 6j. And then negative 4 times 2 times k, that's going to give us negative 8k. And then, so these are the positive ones, the ones that we obtained with the sign. And then we are going to subtract the product that we do in the reverse direction. So j times 2 times 5, that's going to give us 10j. I times negative 2 times negative 4, that's positive 8i. And k times 3 times 3, that's going to, oh, actually it was supposed to be this color instead. So that's going to give us 9k. And all we do here is simply simplify like terms, i's with i's, j's with j's, k's with k's. And simplifying the i's, we get 7i. Simplifying because that's 15 minus 8, that's 7. And then the j's, negative 6 minus 10, that's a negative 16. And then negative 8 plus 9, that's going to give us negative 8 minus 9 essentially, that's a negative 17k. Alright, and that's the cross product. So that means this vector is going to be orthogonal to V and to W at the same time. Let's do the cross product of these two vectors in the other direction. So that's going to be I, J, K. Alright, and instead of having 2, 3, negative 2, I'm going to have 3, negative 4, 5, 2, 3, negative 2. And then I'm going to do the same trick of repeating the first column, the first two columns. Negative 2 times negative 4, that's positive 8i. And then 5 times 2 times j, that's going to give us 10j. And then k times 3 times 3, that's 9k. And then I'm going to subtract the multiplications in the backwards direction. So j times 3 times negative 2, that's negative 6j. I times 5 times 3, that's 15i. And last but not least, k times negative 4 times 2, that's negative 8k. So combining like terms, i's with i's, j's with j's, and k's with k's, well, so that's 8. So for the i's, 8 minus 15, that's going to be negative 7. And then for the j's, 10 minus minus 6, that's a plus 16, that's a 16j. And for the case 9 minus minus 8, that's plus 8, that's a plus 17k. And in this case, well, that's the final answer. If you compare these two vectors, we just showed that property right here that order matters. If you do it one way, you do it the other way, you get the same vector but with opposite direction. See the signs, they are opposite to one another. Let's show this property vector with itself, cross product with itself. It's actually 0, or the 0 vector actually, not just 0. So I, j, k, and then v with v, so that's 2, 3, and negative 2, 2, 3, negative 2. Well, if you have seen properties of determinants before, you can simply say that this is equal to 0 because two rows are the same. But let's suppose we don't know that yet. So actually, let's repeat the first two columns. I, j, 2, 2, 3, 3. So in this case, well, so I times 3 times negative 2, that's going to give me a negative 6i, and then negative 2 times 2, that's a negative 4j, minus 4j, and then k times 2 times 3, that's a plus 6k. And then I'm going to subtract the products in the backwards diagonal direction. So 2 times negative 2 times j, that's negative 4j. I times negative 2 times negative 3, that's minus 6i. And k times 3 times 6, that's 6k. So if we add these vectors, so what do we get? Negative 6i plus minus minus 6i, which is plus 6i, that's 0i. And then for the j's, negative 4j minus minus 4, which is plus 4, that's plus 0j. And then 6k minus 6k, that's 0k. Alright? Essentially, we get the vector 0, 0, 0, and I already used another 0, but with an arrow. That's another way to say 0 vector. All right. Find the magnitude of the cross product VW, well, and see what represents. So the square root of, in this case, the cross product between V and W in that order, 7, negative 16, negative 17. 7 squared plus negative 16 squared plus negative 17 squared. So that's going to be the square root of 49 plus 16 squared, which is 256. And the 17 squared, which is 289. So adding these three numbers together, we get 594. And we can simplify this a bit further. Well, that's the same as saying the square root of 9 times 66. 66 is not a perfect square, only 9, which is 3 root of 66. Units squared. Units squared. Why? Because the magnitude of the two vector of the cross product of the vectors represents the area of the parallelogram that is generated by that. So for example, so this is vector V, and here, for example, this is going to be let me use a different color. this is vector W. So what's gonna happen? So in this case, if we extend this as a parallelogram, something like this, something like that, this value, the magnitude, would represent the area of this parallelogram formed by the vectors in this way. Alright, so this is the end of this video. It's a good place to quit. I'll see you in the next video.